Hi everyone. Today we are talking about the accessory structures of the skin. So hopefully you are already familiar with the integumentary system in general in terms of its basic structure, like the cutaneous membrane and its major functions. And so we are going to dig right in. So just a reminder that the integumentary system is the skin, and the skin consists of the cutaneous membrane. The cutaneous membrane, of course, is the epidermis, which is a stratified squamous keratinized epithelium. And then underlying that is the dermis. And you would have learned that the dermis has two major layers. The papillary layer right underneath the epidermis is loose areolar connective tissue, provides a great and robust source of oxygen and nutrients via the blood supply to the epidermis. And the deeper layer of the dermis is the reticular layer. And of course, that's going to be dense, irregular connective tissue. And then deep to that is the hypodermis, but technically not officially part of the skin. Now we're going to focus on the accessory structures of the skin in this lecture. So we're going to look at the hair follicles, we're going to look at exocrine glands, and we're going to look at the nails. And then we'll finish out by talking a little bit about the effects of aging on the integumentary system and also injury to the integumentary system and how the system handles that. So the hair follicles are actually derived from epithelial columns early on in development. And of course, those hair follicles are going to produce the hairs that protect the skull, but also the hairs that protect that provide delicate touch sensation to most of your skin. The exceptions to that are going to be the palms of your hands and the soles of your feet. So the hairs that you find on your scalp or in your axillary area, those are terminal hairs. They're a little thicker, more coarse, often darker, versus the hairs that you find across the rest of your body. Those are called vellus hairs. They are often much lighter and finer or more delicate. And again, they do provide sensation. So let's just look at some basic structures of the hair follicle here. So here is your epidermis right here. You can see the stratum corneum riding along the top, and then you'd have spinosum and stratum basale here. And you can see that the sebaceous glands clearly are associated with that epithelial tissue. And then here we can see the dermis, and deeper down we can see our hypodermis. So probably in your lab class, you already learned some of the basic structures. So you might already know about the hair shaft, which is what is above the skin. And then you have the root of the hair, which is down in the hair follicle. You likely are aware of the arrector pili muscle, which is a little smooth muscle that's attached to the hair follicle, and when it contracts or shortens, it's going to yank on that hair and create like goosebumps. And it may also play a role in helping to drive the release of the sebum from the sebaceous gland. Deeper down in our hair follicle, we have the root hair plexus. This is a nerve plexus of sensory nerves that surrounds the base of the follicle. So any movement of the hair shaft is going to be detected by that root hair plexus, and that message will go to the central nervous system for interpretation and processing. So getting a little deeper into the hair follicle here, let's actually look at some of the layers that we can find in the hair itself and in the hair follicle. So maybe of interest down here is this hair bulb. So you can see we have this little papilla right here. It's got a nice vasculature. So that's going to be important for delivering oxygen and nutrients to dividing cells, right? This is where hair formation is going to begin right here in the hair bulb, which is this bottom area here. So that's the expanded base of the hair follicle. And that's going to surround this hair papilla where we have that really great vasculature. These are going to be actively dividing cells, and we're probably going to find some melanocytes in there as well. And the melanocytes, of course, are going to lend melanin to the hair, giving it its color. So the hair matrix is where we're going to find those actively dividing basal cells that will ultimately create the dead cells that form the hair. In the medulla, we're going to have a layer of daughter cells. They are coming from the hair matrix. These are still relatively flexible because the keratin is just beginning to fill these cells. And then as they migrate outward, we'll have the thicker layers of the cortex. These are going to be very hardened cells because they are filled with keratin in that cortex. And then as we move up, we're going to find a cuticle, which in this diagram is in purple. And that cuticle is going to be thin but very hard with the keratin that fills those cells. And that's going to create the outermost layer of your hair. So if we move over to this cross section or transverse section of the hair follicle, we can see these same layers. So if we start on the outside, we're in the hair follicle. So this blue layer would be the connective tissue sheath that kind of wraps around the whole hair follicle and separates it from the surrounding dermis. If we move inwards, we're going to find the glassy membrane. This is a thickened basement membrane. The purple layer here is going to be the external root sheath. And then if there's an external, that means there's going to be an internal, and that's this gold layer right here. So from where the pointer is moving outward, that would be our hair follicle. And then if we come back here, this light layer is the cuticle. So that would be that hardened keratin layer on the outside of your hair. And then moving inwards, you'd have the cortex. And then the innermost layers would be the medulla. The cuticle layer, this outer layer here represented with these light cells, this is the layer that if you dye your hair, this layer gets disrupted so that the dye can enter in and change the color of the cuticle and the cortex. But the consequence of that is that it dehydrates the hair and makes it more brittle. Now, how does your hair grow? Well, it goes through a cycle, and that cycle starts with the active phase. This is where the hair is actively growing. On average, the hair on your head grows about a half an inch a month. Some people a little less, some people a little more. And this active phase typically lasts about 2 to 5 years, which means hair could grow anywhere from 12 to 30 inches over its lifetime. Now, some people, their active phase can last up to 7 or 8 years, and there may even be exceptions where it lasts as long as 10, and that's going to impact how long their hair can grow. But ultimately, the hair follicle will shift from the active phase and it will start to regress and slow down and transition into the resting phase. And during the resting phase, what will happen is the hair will ultimately lose its attachment to the follicle. At that point, we call it a club hair. And it will remain in the follicle until that follicle becomes reactivated. And when that follicle is reactivated, it will cause the club hair to fall out of the follicle as a new hair begins to form. So it's typical to lose every single day about 80 to 100 hairs as a result of this club hair loss. More than that would be unusual, but that can happen due to stress or changes in diet or changes in hormone production due to, say, pregnancy or puberty. So you will see some variation in this growth rate or growth cycle depending on age and depending on what's happening in that person's life. Okay, so you have already heard about exocrine glands because in the main tissue types lecture, you would have learned about the different kinds of glands. In the skin, exocrine glands are important. Again, like hair, they are derived from epithelial columns during development. We are focused on two different kinds, sweat glands and sebaceous glands. Within the category of sweat glands, we also have two different kinds, apocrine and eccrine glands. Eccrine glands are also sometimes referred to as merocrine glands, but just for the record, merocrine is a way that glands can secrete. It's like vesicles being exocytosed with the product in them, and both apocrine and eccrine glands use merocrine secretion. So that's a little bit, confusing there that we have two names for it, but If you're aware of it, I think you'll be fine. Sweat glands are going to play an important role in thermoregulation. They can help us cool off by releasing water, and then that water can change phase and take a lot of heat with it as it evaporates. But we also eliminate some salts and other organic molecules through excretion in the sweat glands. Our sebaceous glands are going to be a little bit different because they're going to use holocrine secretion, which means the cell itself will be destroyed in the release of the product. But sebaceous glands are going to secrete sebum or oil that is important in coating the cuticle of the hair and also lubricating the nearby epidermis. So if we look at this little chart, let's just point out that epithelial tissue is going to include all the different kinds of epithelia you already learned about, but also some glands. We have two different kinds of glands, exocrine glands and endocrine glands. Endocrine glands secrete into the blood directly. That includes like the islets of Langerhans that produce insulin, for example. But in the skin, we're interested in exocrine glands, which secrete into ducts, and then those secretions go to where they need to be used. So the two that we're interested in, again, are the sebaceous glands, which will use holocrine type of secretion, and sweat glands, both apocrine and eccrine glands, and both of them will use a merocrine type of secretion to release their product. So here is your typical sebaceous gland. You can see it's kind of fluffy looking because there's a lot of lipid in the sebum that's produced by the sebaceous gland. So it looks a little bit like adipose tissue that you saw in lab because lipid doesn't pick up stain, so it leaves the cells looking very light. So similarly to adipose tissue, we're going to see in the sebaceous gland that because of the lipid in the sebum or the hair oil in this gland, it's going to stain very light and have that frothy look to it. Sebum is a mixture of multiple kinds of lipids, including triglycerides and cholesterol, and then there'll also be some proteins and electrolytes in it. And again, it's important for lubricating the shaft of the hair. It also has some antimicrobial properties, and it will lubricate the nearby epidermis as well. And again, just a reminder, it's a holocrine form of secretion from these glands, so the cells actually burst to release the sebum into the ducts that will carry the sebum to the hair follicle. Apocrine sweat glands are going to be a little bit different. They're going to use merocrine as their method of secretion, so basically exocytosis. We're going to find these in the armpits, around the nipples, and in the groin area. The secretion that they produce is stickier, it's milky or cloudy, and because of the molecules that are in it, bacteria like to feed on this secretion, and when they do and they break it down, it can release a pretty strong odor. What's in the secretion is going to be influenced by the hormones of the individual, and apocrine sweat glands actually also include mammary glands in terms of how they produce and secrete their secretion or their product. Notice in this image over here that around these glands, we can see some myoepithelial cells. These are sort of cells that are capable of contraction. So myo means muscle. So they're specialized to be able to kind of squeeze down on the gland to help release the secretion or product. Your typical eccrine sweat gland is going to just release a much more watery substance relative to the apocrine sweat glands. It doesn't tend to get broken down by bacteria and give off an odor. You're going to find the highest number of these on the palms and soles of the feet, but your whole body has them. And again, these are going to play a very important role in thermoregulation and the excretion of waste, since salts can be released with this watery product. And again, if you look at this micrograph over here, you can see there are also myoepithelial cells, which can help squeeze on those glands to move the product forward and help move it out onto the surface of the skin. Now, your nails are derived from a thickening of the epidermis. So their main function is to protect the tips of your fingers and toes, and really they're just thickened sheets of keratinized epidermal cells. And of course, like hair, they are made up of dead cells that are just filled with keratin. But there's a few structure names that we want to know and be aware of. So if we look at this sort of side view of the fingernail, you can see where the stratum corneum is going to overlie the actual keratinized nail right here. So right here is the eponychium. And you would know it as the cuticle. This is really just a thickened part of the stratum corneum. And then underneath the tip of the nail, you have the hyponychium, which is, again, just a thickened area of the stratum corneum of the epidermis. So those are two important structures along with the actual nail body. And you can see how it forms deeper down in the dermis and then rises out onto the surface to cover the top of the epidermis. That's pretty much the extent of what we need to know about nails. We don't go into them in too great of detail. Now, there are some important clinical correlations we want to be aware of. What happens to skin as we get older? And how do hormones impact the skin? And how does skin repair itself after injury? So let's dig into that. So as your skin ages, a bunch of things happen. We're going to see that there are fewer melanocytes in the skin, which means that melanocyte activity is going to decline. And so we may see that the skin lightens with age. And it also may mean that older people are more susceptible to sunburns. We're going to see that the epidermis becomes drier, and that's because the sebaceous glands tend to secrete less sebum. We're going to see a thinning epidermis because basal cell activity declines. And that's also going to make the skin more prone to injury and potentially infections. And it may also reduce the production of vitamin D3, which I'll talk about. We're going to see a diminished immune response. The number of dendritic cells decreases. We're also going to see a thinning of the dermis. So both the epidermis and the dermis are thinning. Particularly with the dermis, we're going to see a loss of elastic fibers. And so that's going to lead to sagging and wrinkling. We're going to see a reduction in the activity of sweat glands, which means older people are not as good at cooling themselves. And as a result, they can be susceptible to overheating in warm environments. We're going to see a reduction in the blood supply, which of course means that someone may feel colder all the time, but it's also going to contribute to some of these other things like a thinning epidermis and a thinning dermis and a diminished immune response, since with less blood supply, we'll have less oxygen and less nutrients being delivered to cells. We're going to see that skin doesn't repair itself as quickly. We're going to see that hair follicles become less active, and so there may be fewer hairs, thinner hairs, and melanocyte activity, remember, decreased. So we may see that hairs lighten or become white. And we may also see altered hair and fat distribution as a result of changing levels of hormones as well. So a lot of things are happening as the skin ages. There are a lot of hormones that impact the skin. Glucocorticoids, they are an important hormone that help you deal with stress. And one effect of glucocorticoids is it changes how you use sugar. Basically, you'll use less sugar and use more lipid. But glucocorticoids also have an anti-inflammatory effect, which is why they may be important in your stress response. But the consequence of that for your skin is that they actually loosen the connections between the keratinocytes, think desmosomes, and that means that the keratinocytes are not as good at preventing infection since they're not as tightly bound to. So when you are stressed, you are more prone to infection. You've probably heard that, and now you have an underlying reason why that is. Thyroid hormones, they help maintain normal blood flow to the subpapillary plexus. So any changes to your thyroid could impact your hair follicles. Your sex hormones help stimulate epidermal cell division. So if those decrease, that's going to, as we saw with aging, that will have an effect on the epidermis. Growth factors are produced all over the body and stimulate cell growth and cell division. So changes there would also affect the skin. Epidermal growth factors are going to be really important in promoting cell division in stratum basale and accelerating keratin production. So again, just this idea that any changes to these hormones and growth factors is going to affect how the skin functions and and affect its structure. And you can also see down there at the bottom, the growth hormone itself is going to stimulate fibroblast activity and collagen synthesis in the dermis. So if we have a decrease in growth hormone, that's going to have a negative impact on the dermis. So the skin is interdependent with lots of other body systems. And when you get to AMP2, you'll learn about all of these hormones when you study the endocrine system. So this is just a tiny little introduction to how important hormones are for promoting good structure, which in turn allows for good function. Now, I've mentioned vitamin D3. You are going to come across vitamin D3 production a number of times in this course, and this is the first time. So vitamin D3 is an important vitamin for us. It's also known as cholecalciferol, and you have the ability in your skin to use sunlight to convert a steroid compound that's located in your keratinocytes. And with sunlight, you can convert that steroid compound into cholecalciferol. And if you do that, cholecalciferol will travel to the liver, and the liver will convert cholecalciferol into another product. We're just going to call that the intermediary product. And that product from the liver will go to the kidneys, and the kidneys will convert it into calcitriol. So cholecalciferol made in the skin using sunlight and a steroid compound found in keratinocytes will ultimately be changed into calcitriol by the kidneys. That's important because the kidneys can release calcitriol where it will go to the intestines and stimulate the absorption of calcium and phosphate. So if calcium levels in the blood are low, we would want to absorb more calcium from our gut. And the way we get our gut to do that is by having the kidney release calcitriol. But the kidney can't release calcitriol unless it has access to cholecalciferol, which you can only have if you have enough exposure to sunlight to make cholecalciferol. So your skin plays an important role in your ability to absorb calcium from your gut, from the foods that you eat. Now, there is another way to get vitamin D or cholecalciferol. You can just ingest it. The problem is there's actually not a lot of foods that have vitamin D in them naturally. They do include things like shellfish, fish oil, and fish. But a lot of people, like the amount of vitamin D in those foods isn't always really high, and then we don't necessarily get enough of them in our diet, which is why in the US we fortify our milk with vitamin D in order to make sure that kids get enough vitamin D in their diet in case they're not getting enough sunlight to convert steroids in their skin to cholecalciferol. If you don't have enough vitamin D or cholecalciferol, then you could potentially develop rickets, which is a lack of calcium salts in your bones, because the only way that you can absorb calcium is if you have cholecalciferol to make calcitriol to make you absorb the calcium. So anyone that doesn't have enough vitamin D might not absorb enough calcium, and as a result, they wouldn't deposit the calcium in their bones, and they could develop rickets, which creates these kind of soft, flexible bones, and it's evident in the legs that the legs will kind of bow out. This is very rare these days in the US because we do fortify so much of our foods with vitamin D. The last thing I want to talk about is skin repair. The integumentary system is pretty amazing because it can actually function totally independently without the nervous or endocrine system guiding it. And the response to injury is a great example of this local control. So we have sort of 4 phases here. The first one is the inflammatory phase, which is triggered by mast cells. And you should have already learned about the inflammatory phase in chapter 4. So you might want to pop back there and just remind yourself about the swelling, redness, heat, and pain associated with the inflammatory phase and how those and why those things occur. So that would be step 1 in our skin repair. So step 2 would be the migratory phase, and this happens within a few hours of the injury. And basically, we're going to see cells of the stratum basale migrating along the edges of the wound, and they will start dividing in order to replace those lost cells. We're going to see macrophages removing debris, and more phagocytes will arrive as a result of the enhanced circulation from the inflammatory phase in order to help clean up that debris. And then we're also going to see clotting taking place around the edges in order to help isolate that region. And that will ultimately lead to the formation of granulation tissue, because essentially what's happening is you've got cells of the epidermis and cells of the dermis that are all becoming really active in response to this injury. And the combination of the blood clot that's forming, the fibroblasts that are moving in and dividing into the area, whatever the epidermal cells are doing, and then the extensive capillary network, that's going to form that granulation tissue. And that's really important to the healing process. Then we move into the proliferation phase. This can be up to like a week later from the injury. And you can see that what's starting to happen is the big clot is starting to dissolve as the granulation tissue moves up and fills in under the injury. And so we're going to see that fibroblasts are very active, creating a meshwork that the epidermal cells can kind of migrate over in order to help repair this site. And we're going to have a lot of collagen fiber production from those fibroblasts, and the majority of the new tissue that we have forming here is going to be collagen. And so what ultimately we're going to see is that while we are addressing the injury site, the new tissue is not going to be like the original tissue. So then we move into the scarring phase, and you can see that now the clot is totally gone. We do have epidermal tissue over the top of that connective tissue underneath, but you can also see here that there is less of a blood supply, there's a lot of fibroblasts, and there is a ton of collagen. And so this tissue is not going to look the same as it did before. In some cases, in some people, that scar formation continues past where it officially, if you will, needs to be. And so you can see the development of a keloid. This is when the scar actually gets really thick and raises up above the surface of the surrounding tissue. They're often shiny and smooth. They're not harmful in any way. They just might be considered a cosmetic problem, but in other places they're considered, they're actually created on purpose to kind of create body art. So different ways of viewing things. All right, and that's everything that you need to know for accessory structures of the skin.